This is video lesson number 1 for optics. Today's lesson is going to be looking at light, sources of light, how light works, what are the different types of light, what does wavelength, frequency, amplitude all mean, and how do we do calculations using the wave equation. So first of all, there are many different sources of light out there, and so there's a few examples on the page in front of you, and we're going to label them as a few of the different types. So first of all, most of the light on Earth comes from the sun, and light that's produced through heat is called incandescent light. So this is a natural light source of incandescent light. So incandescence. Okay, a regular light bulb would also be incandescence because the wire inside is heating up and producing light. And another one that's incandescence would be like a halogen light bulb. So when you see those long light bulbs in malls and in schools, there's a gas inside that is being heated up to form incandescent light as well. So that's also incandescence. Another major source of light is luminescence. Now, luminescence is basically when something is able to absorb the light emitted from something else and then re-emit it later. So an example here, you've got those little sticky things that you put on, your walls. Okay, and this is called fluorescence. We can also have light being produced from chemical reactions. So there's sort of two types of that. You can have it directly from a chemical reaction, which we would call chemiluminescence. Okay, so if you were to mix two compounds together that produce light, one of those is luminol that does that. You would get chemiluminescence. And a specific type of chemiluminescence that occurs in organisms is called bioluminescence. So there are lots of fungi that bioluminesce and lots of things in the ocean. So these are jellyfish that bioluminesce. So both of these are examples of bioluminescence. We can also get light from things like lightning. So this is also sort of incandescence, but we have specific names for some of these things. So we would call this electrical discharge. So when you see a spark or lightning, it's light from electrical discharge. And then what's probably the most common source of light in your house is through LED lights. So LEDs, which are light emitting diodes, which are sort of like electrical discharge. Light emitting diodes. Okay, so a few examples of types of light. Now, white light, okay, can be split into various colors. When it passes through a prism, okay, which is a rectangular piece of glass. When this happens, okay, this phenomena is known as dispersion. So white light hits the prism, okay, and it's going to be split into different wavelengths of light because they're going to travel at different speeds within the prism. So the shorter wavelengths and longer wavelengths are going to travel faster and slower through the prism, and that's going to mean that they're going to have a different angle from where they hit the edge of the piece of glass. And we're going to talk about why that occurs when we get into our refraction part of the unit in the second half. But basically you're going to have a split making those Roy-G-Biv colors. So you're going to get a red beam, and then you're going to get an orange beam, then a yellow beam, then green, blue, indigo, and violet. So Roy-G-Biv, labeling out your colors with your shortest wavelength all the way to your longest wavelength, all the way to the shortest wavelength. So with the electromagnetic spectrum, we can see not only how the different colors of light have different wavelengths, but also the entire spectrum of light. So not only do we have white light, but there's a whole bunch of other types of light that we can't see, but that you've probably heard of before. So first of all, the electromagnetic spectrum is the range of all possible frequencies / wavelengths of electromagnetic radiation. Okay, and all electromagnetic radiation, no matter the wavelength, always travel at the speed of light, which we're going to talk a bit more about in a minute. So you hear people talk about the speed of light, the fastest thing. So here is our electromagnetic spectrum. Okay, and when we talk about all types of frequencies and wavelengths, frequency is how many wavelengths you can fit in a specific size, or in a specific, like how many revolutions in a specific distance. So this end of the spectrum, okay, is going to have high frequency. Okay, and frequency we show by kind of like a curly F. But the wavelengths are really short, so they're going to have low wavelength. Now, wavelength is written using the Greek letter lambda. So frequency is kind of a curly F. Wavelength is lambda. So at this end of the spectrum, you have really short wavelengths. Now, a wavelength is the distance between two troughs or two peaks. So from like one, there to there is like one wavelength. So everything down at this end of the spectrum have really short wavelengths, so low wavelengths, but really high frequency because we can fit a lot of revolutions in the same amount of space. Versus at the other end, we have low frequency, okay, because you can't fit very many of the wavelengths in the same amount of space, okay, but very high wavelength. So those are shown using the two kind of bars on either side of this picture. Up here, you've got wavelength in meters. So wavelength should always be measured in meters. So you've got really, really short all the way to up to 100 meters long just for one wavelength. In frequency, it's measured in hertz, okay, which are basically revolutions per second. It's sort of like per second. You can kind of think about it like that. And so really high, all the way up to 10 to the power of 20, or down around the 1,000 per second mark. Now, what are all these different wavelengths and how do we categorize them? Okay, and that is into sort of 7 major categories, where we have here in the middle is our visible light. Okay, so all the way from red to purple or violet is your visible light. So we're going to add that label to the top. So visible light is here kind of in the middle. This is everything we see. And we have the colors red, orange, yellow, green, blue, indigo, violet. Now keep in mind that colors in light are not the same as colors in art. So when you learn about the colors in art, you think, okay, it's like a wheel. So you have your 3 primary colors being red, blue, and yellow. And then when you mix red and blue, you get purple. And when you mix, yellow and green, you get, or yellow and blue, you get green, and so on and so forth. But in light, it's not the same because it's not a wheel. It's not connected back to each other. It's basically like a line. So on one end, your violet and your red are never going to like come around and meet each other. They're going to be separated and they're going to go into 2 sort of separate areas. So there's actually no such thing as like pink light. So you get your sort of violet color, which is kind of like a dark blue. And there's no real like pinkish purple light that we can see. It's a mix of other colors. So on the side of violet, so red, blue, indigo, violet, we have ultraviolet. So ultraviolet light is the next one over. That would be, think of, radiation from the sun. So ultraviolet light is why you wear sunscreen. Then after ultraviolet, getting even smaller, are your X-rays. So if you've ever broken a bone and had an X-ray, okay, that's those types of light waves that you can't see. And then the final type that is the shortest with the highest frequency are gamma rays, which are emitted from radioactive material, and they're very harmful. So the more you go towards this direction, the more harmful those rays can be. So gamma rays are really, really dangerous and can cause cancer very quickly. X-rays, you're okay to be exposed to a few X-rays in your life, but you don't want to be X-raying, your body every few days or anything like that, because it can also damage your DNA and damage your cells. Ultraviolet light, again, it's not as dangerous as the other 2, but with lots and lots of exposure can cause things like skin cancer, which is why you want to wear sunscreen. Visible light is safe, and that's what we can see. On the other side of visible light, so we go down towards the other end at the red side, we're going to get infrared. Now, infrared radiation is how heat is sort of seen. So you may have seen in TV shows where they're, hunting or they're looking for the Sasquatch or something. They'll have heat infrared detectors that show you the heat signature of animals and stuff around you. And then after infrared, you have microwaves. Now, microwaves are exactly what they sound like. They are the types of waves that are found in a microwave that we use to heat up our food. And then the last type are radio waves. Radio waves are really, really long, on the magnitude of, up to 100 or 1,000 meters long. So they're, the sizes of football fields and things like that. And that's why they can travel such significant distances. So if somebody is emitting a radio signal from, the center of a town, you can get that radio station even on the outskirts, because the waves are so large that they can travel through lots of things. They're very low energy, so they can kind of go a very long time. Think of it kind of like the tortoise and the hare, like you've got very slow and steady wins the race type of thing happening here. Versus on the other end, these are really high energy and can be very dangerous, but they only travel short distances and they can be stopped by walls and stuff like that. Which is why when you get an X-ray, they'll put like a metal pad over top of you and only expose the part of your body that they're looking to x-ray, and then the pad kind of protects the rest of your body. So those are all your different types of light, and you should make yourself familiar with kind of roughly the order that they're in. So if you were asked, are x-rays shorter than infrared waves, then you would be able to say yes, x-rays have a shorter wavelength than infrared rays. All right, moving on. So coming back to light, what light is and how we give terminology to waves and do calculations with light. Light is a form of electromagnetic energy. Okay, that travels in waves. Now, what is a wave? A wave is basically a disturbance in electromagnetic forces, okay, that transfers energy without transferring any matter. So it doesn't have any weight. Now, a typical wavelength diagram looks something like this, okay, where the top of any wavelength is called the crest, and the bottom is called a trough. So you've got a crest and a trough. A wavelength, okay, is the distance between two crests. So it's a full revolution if you think about it kind of like a circle. So you have to go from one crest all the way to another crest, and that distance is the wavelength, okay, which we call lambda. Okay, and the unit for wavelength is meters. So lambda is, oh, that's a bit too far down. Here we go. Okay, lambda is the wavelength. Oops. Okay, in units of meters. So we always want to make sure we convert it to meters before we do anything else with those numbers. Because sometimes, because wavelengths can range from such tiny to such large numbers, you can get wavelengths in like nanometers or micrometers or centimeters or all kinds of different types of measurements. And we always want to convert it to meters before we do any calculations with it. So that's wavelength. Amplitude, okay, is the height from the rest position, which is this line along the middle. So I'll label that as rest. To the crest. So from the very top crest to the rest position, this is going to be your amplitude. Then our last thing here, frequency, is the number of full cycles in a given time, usually per second. Okay, so this curly F we kind of mentioned before is the frequency measured in hertz. So the wave equation looks like this, V equals F lambda. Now we've defined F and we've defined lambda, but we haven't talked at all about what this V number is. V is the speed of light. So the speed, okay, of the wave in units of meters per second. Now, this equation you'll be using to find frequency, lambda, and speed sometimes, so different rearrangements we can do with that. So if you like to use a magic triangle, here's your magic triangle for this equation. If you're looking for V, you just cover it up. It would be F times lambda, so this is a times line. If you're looking for F, it would be V over lambda, so these are your division lines, if you do it that way. So the speed of light is a specific number. Okay, when we're talking about light traveling through air or through a vacuum. Air is not quite a vacuum, there are particles in it, but because there's so few particles, we would consider it, for our purposes, like negligible, the difference between a vacuum and between regular air. So when we do our calculations with the wave equation, we're going to be looking at assuming that the speed is always the speed of light for now. When we get into refraction and looking at light traveling through more optically dense substances like glass and water, that will change a little bit, and we'll talk about that next week. But for now, we're going to be assuming that the speed of light is going to be as if through a vacuum. So C is the speed of light in a vacuum, and that's a constant. So that means that it's always going to be the same number. So this is always the speed of light in a vacuum. So for our purposes, for most of these equations, okay, V, the speed of light, is going to be equal to specifically the constant C, speed of light in a vacuum for now. So you may notice here that we have a number in scientific notation, so times 10 to the power of 8 meters per second as our speed. When you're doing calculations with scientific notation, it's important that you type it into your calculator correctly. My calculator looks like this, and so it has a button at the bottom for scientific notation. So times 10 to the power of x. So if I wanted to type in this number, I would type it as 3 times 10 to the power of 8, and it would look like that on my screen. But for many of you who have different calculators, it might look a little bit different. If you have one of the blue calculators, then you'll need to use these instructions. So most of you probably have that type of calculator. And you use the EE button. To get that, you're going to press the second function, okay, and then hit the button that has EE on the top. So there's a button that has EE along the top of it. And that's going to put in this sort of E letter into your calculator, and that represents the times 10 to the power of whatever number comes next. So this 3 times 10 to the power of 8 would look like 3E8 on your calculator. Okay, and that's how you type it in correctly. If you don't type it in right, and you do it the long way and you type in, 3, and then you put a times button, and then you put a 10 button, and then you put it to the power button, and then you put the 8, and you do it the long way. If you're trying to do anything with that number, it's going to do the order of operations wrong, and you're going to get an answer that's incorrect. So do not do that. Make sure you're putting it in as scientific notation so that your calculator knows that it's one number, not multiple functions. Okay, we're going to do a few examples here. So calculate the frequency of orange light if the wavelength for orange light is 600 nanometers. So first thing we need to do is write out what we know. So we're looking for frequency, so F is what we don't know. We know the speed of light is 3.0 times 10 to the power of 8 meters per second. So there's our speed of light. And we know that the wavelength, lambda, is 600 nanometers for this orange light. Now, hopefully you remember that we need to have lambda in meters, not nanometers. So we need to convert this nanometers into meters, and that's what this number is here for, to tell you how to do that. So 1 nanometer is 1 times 10 to the power of negative 9 meters, which means that you've got 600 nanometers will be 600 times 10 to the power of negative 9 meters. So you see how it's a 1-to-1 ratio, but truly a number in scientific notation should only have one number in front here. So if you want to take it a step further to be slightly more correct, you can write it as 6 times 10 to the negative 7. So you're basically taking the decimal over 1, 2 spots and bringing that down 2 as well to give you 6 times 10 to the power of negative 7 meters. For our purposes in this online course, I'm not going to be too finicky about how you do this. If you know your conversions well and you're really comfortable doing that, then great, go all the way to 6 times 10 to the negative 7. But if that's really throwing you off and really tripping you up, for now, if you want to just do the 1-to-1 ratio and just add this times 10 to the negative 9 on it to change your units, I'm okay with that for now. So 600 times 10 to the power of negative 9 would be acceptable because you will still get the correct answer at the end. So now we need to write out our equation. So here we're looking for F. So F equals speed divided by lambda. So remember our equation in our magic triangle looks like this. So there's our equation, magic triangle. We're solving for F, so it's V over lambda. We can put our numbers in, so 3 times 0 times 10, 3.0 times 10 to the power of 8 meters per second, divided by 6 times 10 to the negative 7 meters. So now meters divided by meters will be able to cancel out. And we'll be left with per second, which is basically hertz. When you do this division, you should get 0.5 times 10 to the power of 15. When you divide a negative exponent, the symbol changes. So you would go 8 minus negative 7, so that becomes 8 plus 7, which is where the 15 comes from. So double check that your answer makes sense. If you're typing it wrong into your calculator, you're going to get a different number here because it's going to do this part wrong. Okay, now also when we're writing something in scientific notation, really we should have one number in front of the decimal. So I'm going to change this. I'm going to move that decimal place over one more time and take 5 times 10 to the power of 14 hertz. So when I move the decimal place in that direction, this number comes down 1, just like we did before. So now we've got 5 times 10 to the power of 14 hertz. Finish this question off. We say, therefore, the frequency of orange light is 5.0 times 10 to the power of 14 hertz. Now, I've written, you'll notice 5.0. Really, because there's no decimal on that number, it should just be one significant figure. So I'm going to change that to just 5. My apologies. Significant figures is something that you'll learn about in grade 11 chemistry and grade 11 physics. But for grade 10, we're not going to worry about it at all. All right. For the next 2 questions, I'd like you to give them a try on your own, and I will provide full solutions so you can check your work. So give those a try. Start by writing out what you know, rearrange the equation to solve for what you're looking for. So in question number 2, you're going to be looking for the speed, and in question number 3, you're looking for the wavelength. So you're going to be rearranging that equation a couple different times. So give that a try, and then check your answers with the answers provided in the answers folder. Okay, and then you have some practice. So on page 6, you're going to complete this homework practice and submit that for feedback and completion marks.